This is the Levitating Balloons experiment for LB-274. I'm James.
I'm Rohan.
I'm Cody.
So some main ideas we took into this lab were Coulomb's law and R hat, which is part of Coulomb's law. Coulomb's law helps to calculate the force electric and also states that like charges will repel each other while opposite charges will attract each other. R hat is a unit vector which points the direction from Q. It states that if the direction of force is opposite of R hat, then there will be an attraction. If the direction of force is the same as R hat, there will be a repulsion. A couple assumptions we took going into this lab were that when we tried to charge the balloons, we rubbed them a same amount of times to give it a same amount of charge, and we also said that air resistance from to the balloons was negligible, as well as friction caused by the table.
For the models, we looked at energy bar graphs, system schema, and force diagrams. For the energy bar graphs, the total energy shifts from potential when the free balloon is held next to the fixed balloon to kinetic as the free balloon is repelled away. There's a high potential energy at first when they are held next to each other, and once the free balloon is released, the kinetic energy begins to increase as it accelerates from the being repelled. This causes the potential energy to decrease since the energy is conserved in the system. For the force diagram, the contact and gravitational forces are equal, so the electric force in the x direction is the only force causing movement between the balloons. Before the free balloon is released, there's a high potential energy, so the electric force is very strong between the two balloons. After they are released and the potential energy is converted into kinetic energy, the electrical force decreases until the balloons come to rest.
After charging the balloons, we dropped the free balloon and measured its acceleration in the x direction using tracker. For our calculations, we set force kinetic equal to force electric using force kinetic's instantaneous acceleration measured on tracker, as they are the forces that act in the x direction. We then solved for Q using Coulomb's law and converted from coulombs to electrons to determine the number of electrons that were transferred.
After completing the lab, we encountered a couple limitations. One limitation was that after charging the balloons, they became attracted to neutral objects. So this could have slowed down the acceleration of the free balloon, as it could have been attracted to the surface of the table. Another one was that there was limited amount of motion that the balloons exhibited. This gave us a small amount of interaction to observe what was going on, and it made it harder to track the acceleration through tracker. And the third problem that we encountered was that the charges, after rubbing it with a scarf, the balloons, may not have been consistent throughout the experiment. So some things we took into account to make the lab more accurate was to create a track for the balloons. We also tried to rub each balloon an equal amount of times. Tried to hold the balloon on opposite sides when we created the charge. And we tried to move all the neutral and charged objects out of our system, and we utilized tracker to get the best results for calculating acceleration.
When the two balloons were given an equal charge, they were repelled from one another. This was seen when solving for R hat. The force electric was in the same direction as R hat, which indicates a repulsion force. We calculated out the charges of the balloons and found that each of them had a charge of 8 times 10 to the negative 6 coulombs, and also found that the number of electrons transferred between the two balloons was 4.993 times 10 to the 13th.